Yeah, so we will start in a few minutes. Let's wait for a few others to join. Okay, let's start today's discussion. So today's topic of discussion is assignment number 9. Okay, so today's topic of discussions are the interior points, boundary points, okay, uh, and bare category theorem, complete metric spaces. So we'll start one by one, and then we will discuss each and every point. In between, if you have any question, you can ask. You can stop me, and if you have any other doubt as well, you can ask me. Okay. So let me start with writing this question number one. Let int a denote the interior set of a set A in a topological space X. And which of the following are true? Option A, if X is R and A is Q, then interior of A is empty. Option B says if X is R and A is Q, then interior of A is Q itself. Option C says if X is R, if X is R square and A the set of all points in R2 such that x and y coordinates are same, then interior of A is empty. Option D says if x is your ordered square, okay, the ordered square with the ordered topology, and A is a collection of all points of type 1 by 2 comma y, where y varies over the interval, then question is that interior of A is empty. Okay. So again, as always, I will wait for a few minutes for you to think about this question and let me know your guesses, and then we will discuss the solution of this. Okay. Okay. Option A and option C are correct, right? That's what you are saying. Okay. Let's explore the answers. Uh, let us see the explanation of this question. So A denote interior of A denote the set of all interior points of A of a topological space X. Then which of the following are true? And if I start with X with the real line and A with the set of all rationals, then the interior of A is empty. Let us first look at this. Now, what is the interior point? Let us first recall that. So we say a point P in A is an interior point of A if there exists a neighborhood, there exists an open neighborhood U of P contained in A. Okay, so such points are called interior points. All right. Now we just need to see whether it is true for the option A, option B, and option C and D. So for option A, when you have rational points, when A is set of all rationals in the space of reals, then any open neighborhood containing containing rationals. And what is the topology that we are looking into? We are looking. So R has the Euclidean topology on it. So any open set, so any open neighborhood of point P in Q has is an interval, is an open interval, A comma B. Okay, P containing A comma B. Now clearly, now A comma B does not contain entirely in Q because there are irrational numbers as well. Okay, and this yeah. So there are multiple reasons. Number one, uh, because open interval A comma B is uncountable, is uncountable, whereas Q is countable. Uh, okay, so it can't be a subset of Q. Mm. Thus, uh, any rational is is not an interior point of Q. Okay, so option A is correct. So the interior of A is empty set. So since A is true, so B has to be wrong. So B is wrong. Now option C. Option C says that X is R2 and A is a line that passes through origin and the line determined by X and Y equal to X and X equal to Y. Then the interior of A is empty. Okay. So this can be seen by drawing this. Uh, so this is X equal to Y line. Okay, and this is the R2 plane that we are looking into. And now, if you take any point in this line, P, so what topology are we in? We are in the product topology. Okay. And in the product topology or in R2, Euclidean topology, the neighborhood will look like this. So it is an epsilon neighborhood ball centered at origin, centered at P. Okay. And we can clearly see that this ball is not part of the this ball is not included in the red line. Okay, it intersects the red line, but it is not part of. It does not entirely included in the red line. So, and this is true for any point uh, lying on this line. Okay, therefore, interior of uh, A is again empty because it does not contain any open neighborhood of any points, any of its points. Okay, so option C is also correct because the interior is going to be empty. Option D. Option D is given to be the ordered square with ordered topology. So in the ordered square, we have this square. Okay. So this point is 1 0 comma 1. This point is 1 comma 0. This is 1 comma 1, and this is 0 comma 0. And the square that we are looking in, oh sorry, this point is 0 comma 1. This point is 1 comma 1. This point is 1 comma 0, and this point is 0 comma 0. And the square that we are looking in is covered by black lines from two sides and red lines from two sides. Okay. So this is, and when I say that it has a order topology, that means uh, any point. So how does an interval look like? So the order is given by a comma b is smaller than x comma y if a is smaller than x, or a is equal to x and b is smaller than y. Okay. So for example, if I look at this point, if I look at this interval half comma 1 by 3, then 1 by 2 by 3, 0. So this will be, so let's say this is half, this is 2 by 3. So this includes, it starts from here, it goes and it comes back, and it is again again go and come back, and it ends here. So this is the interval that I'm looking into right now. Okay. So this is all included. Okay. Yeah. And now if I come back to the question that we had in this question, uh, yeah, the A is given to be half comma y. Okay. So let me just remove this. So it is half comma y. So this is the interval that we are looking into. So A is nothing but the open interval. And if I look into any of the point, if I look into any point in this, let's say this point, and I want an open interval to be included, so the open interval that will it contain will be this. Okay. So in more proper way, let P be an element in A. So P must be this for some y naught in the interval. Okay. All right. And now half comma y naught, half comma y naught is contained inside this neighborhood, which is given by this open interval, is given by, okay, some plus epsilon and minus epsilon in the y direction. Okay, this is clearly included in this, and this is completely contained inside A. Okay, so um, thus uh, P is an interior point, and since P is arbitrary, um, A is interior point of A is nothing but the interval given by this. Okay, so option D is also wrong because it says that the interior of A is interior of A is uh, trivial, but the interior of A is non-trivial, and it is given by, except the end points, which is half comma 0 and half comma 1. Except these 2 points, every other point is in the interior. Okay, this is what we can show. Now, question number 2. Do A denote the topological boundary of a subset A in topological space X, then which of the following are hold? Option A, if X is an interval and A is Q intersection with the interval, then boundary of A is empty. Option B, if X is an interval and A is intersection of the interval with the Q, then boundary of A is the whole X. Option C, if X is an interval and A is singleton half, then boundary of A is X. Option D, if X is an interval and A is singleton, then the boundary of A is A. Okay. So let me start with uh, saying what is a boundary of a set. So boundary of a set, topological boundary of a set is defined to be A closure intersection with complement, closure of A complement. Okay. So for example, if A is 0, 1, then A closure is close 0, 1. A complement is going to be this. So A complement closure is going to be precise, is going to be minus infinity to 0 closure, union 1 to infinity. So intersection of both will be equal to 0 and 1. Okay. So again, let's wait for a few minutes for you to think about this problem and then we will discuss the solution. Okay, option B and D, right? Yeah. So now let us look at the solution. Um, so if X is given to be the open interval, sorry, closed interval, and A is Q intersection with that, then the boundary of A is what? Okay. So for A, if then A closer is going to be what? Because in the intersection, A closure will include all the limit points of this set, and rationals are dense in nature, so it will include the all points. So this will be whole of this will be whole X, right? Now, what's the complement? Complement of A is set of all uh, irrationals in the interval. All right, and now what is the complement? What is the closure of that? That will also give you the whole space. And if you intersect both of them, since both are same set, so you will get the whole space X as the boundary. So the boundary of A will be the whole space X. So option B is correct. And this also implies that option A is incorrect. Now let's look at C. So in C, we have X to be 0.1 closed interval, A singleton half. Okay. Now what is A closer? A closer is again half. Now what is A complement? A complement is 0 to half union half to 1. All right. Now if I take the closure of this, now this will include the whole space. If I take the intersection of both of the thing, I will get singleton half, which is equal to A. So the boundary of A is equal to A. All right. So option uh, D is correct. So option um, B and D are correct. C and A are wrong. Okay, good. Question number three. It says that let X be a topological space and A is a subset of X. Now, which of the following are true? Option A, the boundary of A is equal to boundary of the complement. Option B, if boundary of A is equal to A, then A is equal to A closer. Option C, if boundary of A is equal to A, then A is equal to interior of A. And option D, if X X is in the boundary of A and U is a neighborhood of X, then U intersects A and U intersects A complement. Okay. Again, I will stop for a few minutes for you guys to think about this question, and then I will discuss the solution. Okay. So now let us look at the solution to this question. Now, since boundary of now let us first see option A. Boundary of A is equal to boundary of A complement. Now, what is boundary of A? Boundary of A is nothing but A closure intersection with A complement closure. All right. And what is boundary of A complement? A closure closure of A complement intersection with A complements complement and then closure. Now, what is A complements complement? It is X minus A complement. Now, what is it? Which is X minus X minus A. So it will be A. All right. So we will get A complement intersection with A closure. So it will be boundary of A again. So boundary of A is equal to boundary of A complement by the definition. Okay. Now, if boundary of A is equal to A, then A is equal to A closure. So for that, we use a theorem which can be stated as follows. It is part of the lectures. Let A be a topology subspace of X, then interior of A intersection with the boundary of A is empty. Interior of A union with the boundary of A is equal to the whole A closure. Okay. Now if we start with, so the idea is to use this theorem. Okay. So now if boundary of A is equal to A, then um, then interior of A intersection with boundary of A will be interior of A intersection with A to be empty. And now we know an interior of A is a subset of A. So this implies that interior of A is empty. If interior of A is empty, then by the second probability, we have which is interior of A union with boundary of A is equal to A. So we have empty union with boundary of A is equal to A closure. So this implies that, okay. So option B is correct, but option C is wrong. Okay. Now let us see option D. So option D says that if X is in the boundary of A, uh, and U is a neighborhood of X, then U either intersects, then U intersects A and A complement as well. Now, because X is in the boundary of A, that means X is in the intersection of A closure and A complement closure. All right. So now, when X is in the A complement closure, what does it mean that? It means if I take any neighborhood, any open neighborhood U of X, then U will intersect A, okay, because X is in the A closure. This is equivalent to say that X is in the A closure and X is in the A closure of complement. This should be non-empty, and basically there is an open neighborhood. Similarly, U complement with A intersections A complement, U intersection with A complement is also non-empty. So together, together, this will imply that yeah, this is what we were asked to prove. So yeah, so there is an open set, open neighborhood of U that intersects with both. Okay, so option D is also correct. Option B is correct. Option C is wrong. Okay, okay. Now let us discuss another question. Question number 4. It says that let X be a topological space. Then which of the following are true? Option A, interior of A intersection with boundary of A is empty. Option B, if A is open, then interior of A is equal to A. Option C, if interior of A is empty, then A is equal to enclosure. Option D says if X does not belong to interior of A, then either X is in the complement or X is on the boundary. Okay. Again, let's wait for a few minutes for you to think, uh, and then we will discuss the solution. Okay, now let's look at the solution. Uh, so this option is true. This is from one of the result uh, in your lectures, and this is already we have written down over here that interior of A intersection with boundary is empty. So A is already true. We know that. Now, if A is open, then then interior of A is A. Uh, this is also one of the definition of the interior of the open set. Okay, that it contains every point is an interior point. Okay, or another way we can also say this way: let A be a subset of X, then interior of A is the largest open set contained in A, that is interior of A is the union of all open sets contained in A. And now, since A is open, we can write is equal to A. So this is true. For option C, if interior of A is empty, then A is equal to A closure. This is not true. For example, uh, let's take A to be Q. Okay, and if you take its closure, it's going to be whole R. Okay, but interior of A, that is interior of Q, is empty. So uh, yeah, so this implies that A is not equal to A closure, which is Q, because Q is not equal to R. Uh, we know that R is uncountable and Q is a countable set. Okay, so C is not true and Q is an counterexample to that. Let's say D. If X is not an interior, if X is in the interior, it's not in the interior, then this implies that X is either X is if X is not an interior, then either X could be in A or X could be in A complement. All right. And since if um, X is not an interior but in A, so if X is in A, sorry, if X is in A minus interior, okay, and we know that interior of A intersection with boundary is empty. All right. So, so if X is not an interior, so it has to be in the boundary, or if it's in, or either it's in the complement of A. So option D is also correct. So ABD is correct answer. Now let us write down the question number 5. Which of the following which of the following subspecies of R bare? Okay. Option A Q. Option B R minus Q. Option C union of the open intervals from n to n plus 1. N is in Z. Option D close interval 0, comma 1. Okay. So um, so what is bare space? We say a subset A is bare space if it is a countable intersection of closed sets with non-empty interior. Sorry, countable union of, yes, countable union of closed sets with non-empty interior. So there, so that the space interior is also non-empty. Okay. So with that definition, for example, Q can be written as union of countable singletons. Okay, where each Q is a rational number and Q is a countable set, so you can number each of the rational in a countable manner. Okay, with a countable index set. And now singletons are closed in the subspace topology on Q induced from R. Okay, and it is a countable union, and the interior of Q of singleton Q is empty. Okay, right? So the interior of singleton is empty and they are closed set. So it is, so there exist, uh, yeah, so there exist, yeah, so there exists a set, there exists a countable collection of closed sets with empty interior. Okay, such that, but their interior of the union is, but interior of Q is Q in the subspace topology. So yeah, so A is not bare space. R minus Q, it is already part of the lecture series that it is a subspace, it's a bare subspace. And why union of intervals is a bare space? It is because of the result, because of this theorem that says that uh, yeah, it is because of this theorem which says that if X is a bare space and Y is an open subset of it, then Y is a bare space in the subspace topology. Or in our case, we will take X to be R and Y to be R minus Z, which is nothing but the union of the intervals, countable union of intervals. All right. So the countable union of intervals. So any arbitrary union of open intervals is open. So Y is open and it is a subspace of a bare space. So thus the subspace is also. So Y is also a bare space in subspace topology. Now for the option D, we use the bare category theorem. If X is a compact first order space, or if it is a complete metric space, then X is a bare space. Okay. In our case, closed interval 0, 0.1 is a compact Hausdorff space. It is also complete metric space under the usual metric because every compact subset uh, of a complete metric space is complete. So closed interval 0, 0.1 is a bare space. Okay. So because of this, option A, C, D are correct. Except option A, B, C, D are correct. Yes. Okay. Question number 6. Which of the following are complete metric space? Option A, close interval AB, 0, 1. Okay. Again, uh, let's wait for a couple of minutes for you to think about this question, and then we will discuss this question. And for the definition of complete metric space, we say a metric space is complete if every Cauchy sequence converges. And what is a Cauchy sequence? A sequence is called Cauchy if for every for epsilon greater than 0 there exists an integer n, natural number n, such that for all nm greater than equal to n, uh, the distance between xn and xm is smaller than epsilon. All right. So this is a Cauchy sequence, and this is a convergent. Whenever Cauchy converges, such metric spaces are called complete metric space. Yes, actually, you are correct. Uh, Now, why option A? Because it's a compact subspace. Compact subspaces are closed, are complete. Okay. So since is a compact metric space, it is complete. Option B, Rn, is also complete. Okay. And the reason follows from the Euclidean, the completeness of the R. Okay. Option C, Q is not complete because there can be a sequence which converges to irrationals. For example, if you consider this sequence, which is 1 plus, consider this sequence, then this sequence, easy to check that it is a Cauchy sequence. But this xn converges to rational to E, okay, because it is nothing but the expansion of E. And E is a rational number. E is not a rational number, so E is a rational number. So um, it is not. So thus Q is not complete. Similarly, option D. one consider sequence xn in R minus Q as x1 to be root 2, x2 to be root 2 times x1, okay, and so on. And for xn, we can define it to be xn plus for all n greater than equal to 2. All right. Now, clearly, this sequence is Cauchy. Okay. But this sequence converges to 2, which is a rational number. Okay. So option A and B are correct, but C and D are wrong. Okay. Question number 7. Uh, Again, the question is which of the following sets are G delta sets, subsets of R? Now, what is a G delta set? A set G, a subset G of R is called G delta if G is nothing but the union is the intersection of UN, where UN is open for all natural numbers. Okay. Again, let's uh, some time. Let me give you some time, and then we will discuss this question. Okay. So so for example, for R, option A, R, one can write R as the intersection of R. Okay. For all, you can take all UN to be R, and then R can be written as the intersection of R counter element. So R is a G delta set. Now option B. Option B is zero, singleton zero. Now singleton zero can be written as the intersection of the open intervals minus 1 over n to 1 over n. Okay, and varying over natural number set. Okay, so it can be written as the this thing. So zero, singleton zero is also a G delta set. Option C is the close interval 0, comma 1. Now this can again be written as the intersection of minus 1 over n to 1 over n plus 1. Okay. So this each of the subset contains closed interval 0, comma 1 and has the intersection. Okay. Um, Now option D. Uh, now there is now one way is easy that 0, comma 1 is contained inside each of this singleton. Now what about the other way that 0, comma 1 contains the intersection? Okay. How do we show that? For that, for that we need to say that the infimum of this set 1 over n, the lim 1 over n is 0, and supremum, sorry, and the infimum of 1 plus 1 over n is 1. Okay, so uh, yeah, so from both of the side, since we are taking the infimum, so the intersection, sorry, this 1 over n is the supremum of 0 is the one supremum of 1 over minus 1 over n. All right. So from both of the side, we need to look at the infimum and supremum, and they those turns out to be 0, 0.1. So everything in between will be lied inside the intersection. Okay. So that's how you can prove that the other way also. For option D, option D is Q. Now, from this theorem, that every dense G delta set is uncountable in R. Okay. So from this, we know that Q is a dense set and it is not uncountable. So this implies that Q is not G delta set. Okay. So option A is correct, option B is correct, option C is correct, but option D is wrong. Okay. Any other question from your side? If not, uh, then we can stop today's discussion here.